I just before I go into what is UCIe, just a quick background on what is a chiplet. So basically, chiplet is a silicon die with a defined set of features, and it has an interface to connect to other chiplets. So in most cases, the chiplet standalone isn't a full-featured product. It just has a partial set of features. It needs to be combined with other chiplets to have the full product. So multiple of these chiplets are combined into a single package to provide the full functionality of the product. So the picture at the bottom, you can see, a monolithic die includes everything that's required for the product in one single die, and it's much bigger. And here's an example of what AMD did in the first generation EPYC. Basically, this monolithic was broken into 4 identical dies, and then there were connections to hook these all together. Incidentally, in this, it was split differently. Instead of every chiplet, so here there are 4 chiplets. Each chiplet had some CPU cores, a memory controller, and then some I/O, and then the connection points. In the next generation, it was split, where all the CPU cores went on individual chiplets, and all the other I/O and memory stuff went into the central chiplet that we call. Okay. All right. So like I said, these in the first generation case, each chiplet could be sold as an individual product. But in this generation, basically, the compute dies can't be sold individually. There's no memory. There's nothing else, right? It needs to be hooked up to one of these I/O die chiplets in order to have full functionality. Can mix and match the number of these compute dies, right? So if you need a product with, certain number of CPU cores, then you can choose how many ever chiplets will be connected to this. So you can leave some of these connection points unconnected. And what that changes is, how much, for example, chiplets have still access to the full bandwidth to memory. So, this allows different kind of products to be built with essentially some smaller set of, Lego bricks. That's the idea. So, so what is a roughly every 18 to 24 months, and over the past, I think 4 or 5 years, that's no longer true. It's slowing down. Defect within that die has gone up quite a bit, and therefore you can have situations where the overall yield is low because the larger dies have some number of defects, which makes them unusable. Chiplets, because they're smaller, there's a lower probability of those errors, and also in terms of how many dies you can get out of a single 300 millimeter wafer, that number is up. And therefore, generally, because the chiplets are smaller in size compared to the monolithic, right? You can see here, if you were to pack the same number, this die is much bigger than any of these individual dies here. So because they are smaller, they have much better yield, and therefore lower cost. And also, like I said, if you have a larger monolithic die and one piece of it goes bad, let's say the memory controller or some other, or clock distribution, some major thing goes bad, product lines. So AMD, for example, takes one of these CPU chiplets, these CCDs we call them, and they can be used in a server configuration or a desktop CPU. And you basically do this chiplet design once and reuse it across 2 or 3 different product lines. And you can imagine if you make a chip that has like a few DDR channels, for example, a chiplet with a few DDR channels, you could use it across various product lines. That's the idea behind chiplets. And then they're composable in the sense that you can combine these chiplets in different ways to create different product SKUs. So you can vary the number of each chiplet, or you can vary the type of chiplets, and therefore you can create different sets of products. And then the other big advantage of this is process optimization, where each chiplet could be fabricated on a process that is most optimal for whatever circuitry is going to be on that particular chiplet. And then this has power, and basically that what is optimal could be in terms of power, performance, or cost, which translates into silicon area. So one of the things, going back to this slide, one of the things that we're seeing in the most latest processes is that while the CPU cluster or CPU cores themselves shrink, can benefit from shrinking, from going from to smaller and smaller process technologies, some of these I/O components don't scale the same way. Similarly, large caches don't scale the same way. So even if you were to put one of these memory controllers in this die, the size won't change from one generation to the next, or changes very little between one process generation to the next, because these are analog dominated, and analog circuits don't seem to scale as well as pure digital circuits. So it's advantageous to build these things in an older process because they don't benefit from going to a newer process anyway. Um, and the older process is generally more mature and lower cost. So there's also cost benefit from sticking to an older process. So in this example here, the CPUs moved to 7 nanometers, but the IO stayed at 14, which is couple generations older. So that's the idea behind chiplets. Then the question becomes, okay, we have all these chiplets, that's great. Well, how do we connect all of them together? So far, it's always been proprietary protocols. AMD developed their own, other companies came up with their own way, and because we were just using chiplets between the same company, right? So AMD designed both sides of those products. We could define our own protocol, but there's clearly, you can see there is a benefit to have a standardized protocol, so that you can mix and match these chiplets from different vendors and with different capabilities. So that's kind of the rationale behind UCIe, which stands for Universal Chiplet Interconnect Express, which is a nod to PCI Express. And this is an open specification for die-to-die connections between chiplets. And like I said, the goal is to enable use of chiplets from different vendors in a single package. Just like you can do today with PCIe devices, you can buy any PCIe card from any vendor and plug it into a standard PCIe slot, and it works. So the standard initially was mostly worked on by Intel, but then pretty soon, early on, AMD, ARM, Qualcomm, Samsung, TSMC, all of them joined in this consortium, and NVIDIA and a couple other companies joined a little bit later. So version 1.0 of the spec was released early last year, and the 1.1 spec was just released a couple of months ago. and it's open. You can go to the UCIe website and download them. You do have to give them your email address, as I found out. So what is UCIe and what does it specify? So the UCIe basically specifies both kind of the stack on the physical layer and the link layer and so forth, and also specifies kind of what kind of packaging techniques you would use to combine these together. So the picture on the left here shows kind of the different layers. And so at the bottom you have the physical layer, and similar to PCIe, this deals with all the electrical parts of the connection, voltage and so forth. There are multiple lanes, so you have to train it when you have to go to higher speed. So basically, what training means is you need to find out how much delay there was so that the data and the clock can be aligned, right? So they could be based on the distance between the two chiplets and the resistance in between. There is a time of flight, right? Signal going from one chiplet to another. And so you need to train for that so that your clock and data edge are aligned, so that clock arrives just a little bit after the data arrives, so that on your rising edge of the clock, the data signal is stable and you can latch that data. Uh, so there are some other uh, things that you can put in to scramble and things like this, but some of that is optional. And the way this works is that the sender sends the clock along with the data, and then the receiver uses that same clock to get it. So that's why you have this clock forwarding logic. So one level above is the die to die adapter, and this is kind of your link layer above, and it's basically specifies if you're trying to multiplex multiple signals onto one interface, you do it in this layer. There's retry, so if errors were detected, you send some CRC bits along, and if there was errors in the transmission, you retry the transmission. And then there's link state and power management here. So if the link is idle, then you can choose to limit the number of lanes or go down to lower speed, etc. And then at the top is the protocol layer work. So these two are fairly well defined at the moment. There's still work going on at the protocol level to define how this would work. On the right here are the different kind of packaging schemes on how you would take these different chiplets, which are these dies in this picture here, and connect them together into a single SoC package. What is called standard package is what is now typically being used, and what is this green thing at the bottom is a substrate layer. It's usually some kind of PCB like material, if you will, and you place the dies on top. At Similar to PCB traces, you have wires connecting signals on one die to the other die, and then for the other ones, it will feed through to the bottom, and you will have the pins or bumps at the bottom. And so this bottom part would attach to your motherboard. And so some of these signals from each die would feed through to a motherboard connection, and others will be used for these die-to-die connections. So this is called standard package, and it's relatively cheap, but there are it uses more power, and there's some other limitations with this one. So then you go into these different examples of advanced packaging. And the most common that is sort of the next one that people are looking at is this thing called Silicon Bridge. Intel calls it EMIB, or embedded forgot what that means. Something bridge. Forget what it stands for. But other vendors call it differently, fan out bridge and things like this. But basically, what it is this light blue thing that you see here is another piece of silicon that is embedded into the substrate. So this package substrate and this package substrate are the same, but except of running wires through the substrate directly, you embed another piece of silicon, which is the bridge. And then these wires are similar to wires deposited on any other die. So this is another piece of silicon. Just think of it as being flipped upside down, and the connection is made between this top die and the bottom die, and it's just a sliver to connect the number of signals on this side to the other one. And you have another one for how many ever die to die connections you need. Uh, so this is, one variant of what we call 2.5D packaging. So this is 2D packaging, so everything is in 2 dimensions, and this is 2.5D. There is another version, or sorry, the next step is where instead of having this embedded in the package, you just have a full slab of silicon, and you have the wires through them, and that's this interposer. And then you can go into kind of more esoteric. Um, sort of the only thing that is being dictated here is sort of the pitch, right? So you have to the pitch between these two. The pitch is high because you need to draw these wires through the substrate, but you can go to smaller and smaller pitches since this is all in silicon. But there is no um, what do you say, limitation on what these dies can be, what process node, all that is orthogonal to the UCIe spec.
Okay.
Right. Um, so protocols, right? We talked about that this top layer, which is the protocol layer, is not fully defined. So currently, what the UCIe does is it provides a mapping for PCIe and CXL, so all variants of CXL, IO, MEM, and cache, to allow these to go over UCIe. And this is basically a path for if you have two different chips that are connected by a PCIe link or a CXL link, um, you could convert those two chips into chiplets and put them on a package and connect them over UCIe. So that's the idea for basically taking things that are at a board level today and integrating them into a package level. So that's why the first thing that the UCIe folks tackled was getting PCIe and CXL mapped. So it now also defines something called streaming protocol to map other protocols, but this is essentially, you can just think of it as like, here's a bunch of wires, and you decide how you're going to send your data across these wires and which wire means what, right? So there's this open thing. They call them bunch of wires or sea of wires, is different terminology. And that one, the protocol definition is left to the vendor to define. So it still allows, if AMD or any other company were to define a custom protocol for two chiplets that the same vendor makes, and they think that going through over these one of these other protocols is going to be less efficient, and they can customize a protocol for their particular application, you could still do that, and you can reuse these bottom layers. It's just this layer that would be different. So you can imagine third-party vendors creating IP, or designs for these two layers, and then you can integrate it with whatever you want to do up here at the protocol layer. Uh, and then there's some work that's continuing to define some other protocols for some other common current and some expected future use cases, but those are not released yet. So this is where I think the most of the work is happening. Uh, and so we talked about the use case where everything is within a package, which is this left hand side picture where you have these different chiplets and then you connect them through these UCIe connections. There's also thought given from the UCIe side about how you can extend it off package, right? So they find something called retimers, which are basically adapters to connect it to other kind of things. So at this point, it starts looking like CXL to connect between different chips or different packages or different even board level, right? You can go once you go optical and everything, you can go across a rack. So there is provision for extending this to rack scale connections. But again, those are not fully defined yet, but that's the idea that you can take the same protocol, extend it all the way to a rack in a data center. Uh, and then this is my last slide. So a lot of these I lifted from the UCIe white paper, by the way, which is also available on the website along with the spec. And the so UCIe currently, this is as of 1.0. I don't think this reflects the latest 1.1, but as of 1.0, basically you're talking about data rates up to 32 gigabits per second per what they call lane or per wire, and you have 64 lanes available in advanced package, only 16 in the standard package. And like I said, this is where the if it's a standard package, because these wires have to be uh, going through the substrate, the pitch between two different bumps at the bottom of the chiplet has to be pretty big. So in this case, 100 to 130 microns. But if you use advanced packaging, because now those wires also go through a piece of silicon, your bump pitch is much smaller. And because this has to go through another piece of silicon, uh, the basically the distance, right? If I go back to this picture, so this distance, right, between two dies on a package, on a standard package, this can be up to 25 millimeters. But if you want to do any of these advanced packaging with a slab of silicon underneath, this distance is limited to less than 2 millimeters. And you can see, actually, I didn't include the picture, but if you look at the pictures of the latest AMD EPYC chips, you'll see they're all bunched very closely together. Uh, the other kind of important thing when it comes to chiplets is what we call shoreline or beachfront, and because you have to place these I should have done this better. If I go back to this picture, this is what we call beachfront or shoreline. So depending on how many signals you want to get across, and the pitch, right, bump pitch between them, that defines dimensions of this chiplet. So it can't be less than a certain width if you have a large number of wires, right? So depending on the number of wires that have to connect across these two chiplets, there is this beachfront that you have to determine. So that determines when you design these chiplets, how much area, how much space here do I need to allocate for these die-to-die connections. Uh, so that's another kind of important consideration in the design. And as you can see, the power, what we define as picojoules to send one bit across, um, it's much better in an advanced package, again, because it's going through silicon, and um, and then the latency through this, right? So it's the target is to be less than 2 nanoseconds. I don't believe any of the vendors today have quite reached that level, but that's the goal. And then reliability wise, it's supposed to be very close to being the same as wires within a chip. So very small error rate, but like I said, if you cannot tolerate any errors, then you have CRC and retry mechanisms to replay the transaction, assuming there was some transient error in the transmission. Anyway, that's it. Any questions?
Thank you, Shankar.
That is an
Okay.
incredible standard. What's the time frame for rollout on this, Shankar?
Anybody's guess. I think that is at least I know a lot of the IP vendors are working on building these bottom 2-layer pieces. I know AMD is slowly going to transition from our proprietary mechanisms to go to UCIe where appropriate. Not all products might go, but any place where we want to be able to integrate third-party solutions will certainly go to this standard. I think Intel is also very close to adopting this. I don't know about NVIDIA and some of the other companies, but there is a broad trying to look for the word. Basically, everybody is coalescing around this standard. There were a couple of other things defined before, but I think they have all fallen to the wayside. But it should be coming out in the next few years. It obviously takes a while. The standard just got released. It takes a while for all these designs to be completed and tested and validated. So it'll take a few years, but I don't know the exact timeline. Any other questions? All right, I'll turn it over to Kurt then.
Okay, I don't think I've got my screen sharing working. So what I might do, especially since Professor Jelinski's got a bunch of people queued up, let me try one thing. Let me try this. And then maybe, I might be able to go in a screen share if I do it from my Chrome tab. Let me try that.
Okay, we're seeing it now.
Yeah, let me see if it'll let me slideshow it. Okay, well, let me try this if this works. The reason I'm showing this slide, I was just going to drop it in there. I think we need to have a moment of silence for the final Bertucci's shutdown of the Central Square location, because I got to figure BLU is good for maybe, what do you think, Jerry, about 1,000 pizza over the course of the last 20 or so years?
I'm sure.
Because we used to buy, during the Linux, your Saturday events, right?
Well, many years ago, I was working for a company in Central Square, in Porter Square, and my boss made a reservation at Bertucci's, and we walked over to it. They didn't have the reservation. He mistakenly made it for the one in Central Square, which was brand new at the time.
Yeah.
And at the time, Bertucci's only had 2 restaurants, the one in Elm Street in Davis Square, which was their original, and this one in Cambridge.
Yep. And you know the story about how this came about, right? That's Steve Steve's is famous for an ice cream shop,
Yep.
and he didn't want any competition in Davis Square. So when somebody thought they were going to build a second ice cream shop in Davis Square, he said, "The hell you are!" And he put some Italian food restaurant in there, called it Bertucci's. And of course, nobody remembers Steve's ice cream, but everybody remembers Bertucci's. So that's a pretty funny story.
Well, that was Joey.
Joey, okay.
That wasn't Steve. Steve sold Steve's to Joey.
Okay. And Bertucci was a fake last name, right?
Yes.
Okay. All right. Well, just tell me. I'm flying blind here since I'm in a Chrome tab. So just tell me if this thing's advancing.
It advanced.
Okay. So one era ends where we have moved on from Bertucci's, and we're going to go to, I don't know what we're going to be eating for food in the future, but also all of the bugs in Boston are shutting down. I think BLU is the last of the original lugs. Jerry, do they still have the lug stock or the big lug in Marlboro that you used to arrange with all the local lugs?
No, but I think the New Hampshire lug is still working.
Oh, okay. All right.
When did they change the name?
The what?
It used to be the Boston User Groups, and now it's Boston Unity Group.
No,
that is no. I have actually. Boston User Group is actually paying for our server.
Oh, so it's a different bug.
Because I have money there, and that was the way it was arranged in the first place. And the BLU has as much money in its treasury as Jabber has in his checking account.
Yeah, and BMUG is now Boston BBS. Now, if that isn't a legacy URL, I don't know what is. All right, so I'm not going to touch, and thank you, Shankar. That was about as good of a segue as I could have possibly have predicted. I'm not going to talk about the Compute Express link standard today. I think what I'll do, especially if Jabber is looking for a speaker November or December, I'm coming back from another big CXL event. CXL Forum is going on this week at Open Compute at Meta Open Compute. And so there's going to be a bunch of new standards and discussions and announcements over the course of the next 2 weeks. So when I get back from the CXL BOF that I'm going to November 9th, I think it is, maybe I'll be able to talk. And I could probably fill 2 hours at that point. I can not only give a CXL tutorial, but I could talk more about how CXL is going to impact our immediate future. So that's why I'm going to tear through the spec. I'll be even lighter on the spec with this bunch of slides than, but like I say, I'll hit. Shankar briefly touched upon the 3 important sub-protocols: CXL.mem, CXL.io, and CXL.cache. For my money, and especially now with the CXL 1.1 standard available in the wild, and to a lesser extent, CXL 2.0 available in the wild if you buy certain motherboards, it's all about the CXL.mem. So that's kind of what I'm going to be talking about. And in particular, as it applies to high-performance computing, supercomputing, university research computing, you take a place like the 5 research universities in Boston. We're all members of the Massachusetts Green High Performance Computing Center. We get to log on and use the supercomputers there. And not only is it very memory centric, how we have to describe our jobs and our batch files, but almost everything's memory bound. If you know anything about how to tune your codes, you quickly discover that application parallel, data parallel. You discover very quickly that if you want to maximize your time on these supercomputers at these universities, especially the university ones that have a huge data center associated with them. University of Texas has TAC. UCSD has the San Diego Supercomputing Center. There's places you can go where you can request a job, put it into a queue, and almost everybody is subscribing. This is the NSF Access /Exceed Campus Champions list, and almost everyone, I would say 90% of all the sysadmins and operators there have subscribed to the Slurm standard as their queuing system. And so Slurm has a very rich ecosystem. You can be very granular. You'll see that I pulled up a page there from the MGHPCC TXE1, otherwise known as MIT SuperCloud. Now, that tells you how many CPUs you could access, which you're sharing with another 1,000 people, probably at the same time you want to access it. But if you know what you're doing with your batch jobs, and you've worked out some deal with the sysadmins, mostly by taking higher level remote courses and proving to the sysadmins that you know how to describe a job and how to submit it as a batch file, you can get access to some pretty heavy duty resources, either a ton of GPUs simultaneously, or what's in much more abundance is a ton of CPUs for long periods of time. If you've got a 3-week job, you can request that. You have to probably qualify by taking these little mini courses, and so what they'll do is at a place like at SuperCloud is you'll go through this effort and you'll either describe in your batch file, which it probably just won't sail through. You'll hit go and you'll probably get a job ID back. But what's much more likely is you'll have some interaction with a sysadmin, and they'll look at your SBatch file and try to refine it a little bit more, tell you how to break it up into jobs, defining nodes, full nodes, threads per node, possibly memory per thread. But generally speaking, what the sysadmins tell you at these supercomputing centers is, look, if you want more memory, just request more CPUs. That's kind of the shorthand, what they're doing now, because like I say, there's an imbalance right now, especially given what has happened with the supply chain over the last 2 years, between how many CPUs a university data center can offer you and how many GPUs they can offer you. And there's a lot of contention. We have some defined rules on who gets better NICE levels, and there's a whole raft. I won't get into too much of that right now, but I will get into it when we start talking about some of the fine-grained memory allocation stuff that you can do with either by yourself outside of a queuing system in CXL, or what's even better is some of these internals in either in Slurm or in some of the other queuing systems. Like I say, most of the research computing, the university associated research computing departments I know of, they've all kind of migrated to Slurm because of the rich ecosystem. It started out as open source, and people have built in their extensions, and as a new tech comes out, you can take advantage of some of these open source editions. So I've lost. Yeah, see, when I imported into docs, it kind of ate some of this. But this was my list of conferences that are either talking about CXL now or have always been talking about memory. Now, all the things that we had workarounds for prior to the Beowulf era are now back in play, because if you've got an application that will grab as much memory as you can give it, and you need 4 terabytes, you can get that now through CXL. To a great extent, you can get it now through the CXL 1.1, which, like I say, you can buy a commodity server right now that'll support that protocol, and it certainly is available under CXL 2.0. If you've got these, CXL 2.0 requires PCI Express 5. Now, that doesn't describe too many motherboards right now, but if you go out and buy a system that has PCI Express 5, you're almost certainly able to run CXL on it, in which case you buy CXL enabled PCI host adapters, and you'll be able to access the RAM on those cards if they're a GPU or a DPU or whatever, and it will it will present itself to the host operating system as system RAM. So if you've got a job that needs 2 terabytes of RAM and you've got that spread over 8 PCIe 5.0 cards, CXL enabled host adapters, then you can run it. And I think like I say, if I'm doing this again before the end of the year, I'll be able to live demo some of that, because most of these, all the products that I know will support CXL 2.0, some of them will be available after November 12th, which is when they're going to be announced at IEEE Supercomputing in Denver. So now I have a couple of other ones. The reason I put the RISC-V focused conferences in there is because the RISC-V folks, especially the HPC RISC-V devs, are very interested in these extended memory addressing schemes. Certainly, you're not buying a system now that'll give you, even though you've got a 32-bit processor, you're not getting, or excuse me, a 64-bit processor, you're not getting 64 bits of memory. But you can with some of the, there's an SV57 and SV64 and SV128 extension in the RISC-V developers are doing. You can get that now if you're totally cool with running it on an FPGA, but I think you'll probably see that in silica pretty soon too. And then there's 2 more conferences in there. The Boston Area Architecture Workshop that Professor Jelinski and I run. We didn't do one this year, and it doesn't look like we'll be able to make it this year, but maybe we'll fold it into Latch Up, which is coming to Massachusetts sometime next year, probably March, but stay tuned on that. We'll have insights into that here pretty soon too. The other link I put in there, the bit.ly Princeton Computer Architecture Day. This is a guy, Professor Wentzloff, down at Princeton, invites. It's pretty much open to local academics that want to come and bring their grad students and their advisees and sit in on his. I don't think he's the head of the department, but he's got a couple of really interesting architectures that he works on down there. Open Python, and then he does quite a bit with RISC-V as well. So I'm sorry that I will move on from this page, but the paper counts in Compute Express Link have dramatically. If you had done a search for Compute Express Link at IEEE Explorer a year ago, you wouldn't have gotten any hits. Now you got 588. Okay, so PCI host adapters. If you have a code and you're like, hey, I want to run this on a GPU, let me see what if I can get a computational fluid dynamic code or a QCD code or something. Let me go out there and find out what community supports this and how to get it and how to tune it. Well, certainly NVIDIA used to hand out a little green magazine that had all the codes that they have certified there's a CUDA port for. And I believe to a lesser extent, you can probably get this for ROCm HIP for the AMD Instinct line of GPUs. You can find out what codes have been certified to run on their tech. So if that's what you're interested in, if you want to wait around for a year and a half for to get an NVIDIA GPU, then good luck to you. However, I'm going to have to come back to this slide. However, if you've got a C or C++ code that you want to run today, and it only runs on CPUs, and that describes a lot of codes. I believe WRF, weather reporting and forecasting, which is an extremely popular code. I don't believe there's a GPU port for that. I guess there's some parts that just don't, the intrinsic parallelism was kind of hard to coax out of WRF. That code's been around a long time, certainly more than 20 years old. So it preceded GPUs. It's hard to get that code to run on GPUs, but it's not hard to get it to run on CPUs. It's just that we didn't have access to huge chunks of memory and large CPU counts until now. And so you can go out to a site and download the code. This one here is Open Novation. Myself and some of the students run this one, and we're trying to update it and pre-build some binaries for particular architectures and distros. We've identified over the course of the last, here again, more than a dozen years, every time the Student Cluster Contest announced a mystery app, In the old days, it used to be one that had already appeared previously in a student cluster competition. Now they've kind of gotten clever. I think they figured we were looking at pre-compiling some of these things from previous years. Now we were doing this mostly as an exercise on how to get smart on optimization and profiling and learning some of the different libraries that you want to use when you're preparing for the student cluster competition. And it's a good exercise. It's just that we kind of had a lottery to see if we could actually somehow figure out what this year's mystery app was going to be. And I don't think we ever got it right, but we certainly got pretty handy with some of the codes that made multiple appearances in the student cluster contest. So our group has been talking about putting together a CXL supercomputer for two reasons. Mostly to follow along with the spec and possibly build it big enough so that it looks a lot like this particular graphic here is a photo of the D.E. Shaw Research Anton and Anton 2 supercomputer. Now, when D.E. Shaw built this, he was targeting a particular protein folding problem, and he knew that this system was going to be air-gapped to anything, to the internet and whatever. So he said, okay, well, I don't know if I need to subscribe to standards all the way around. He had a mixed precision problem being solved by a Tensilica chip in this design. So his board would have a Tensilica chip to handle part of his calculation. And he was like, okay, I don't know if this really lends itself to general purpose. You can get time on this supercomputer at the Pittsburgh Supercomputing Center. You put in a proposal and you learn about the particular curious ways that you have to describe your job and tune your code to run on it. But what I think is interesting about this and why it would be a good tail to build around for the CXL supercomputer is they won the Gordon Bell Prize that year. So that was interesting two ways. They so he not only did good, he solved a protein folding problem at about 10 times the speed of a commodity screensaver, no matter how many processors it was running on. But he also did well. I mean, this is a company that trades on Wall Street, and they wanted to find out how to tune particular algorithms, speed up high throughput codes and things like that. So kudos to him for solving a couple of our problems at the same time.
I mean, D. Shaw was a chemist by training.
That's right, and a professor at Berkeley or something, right?
Yeah.
Okay.
And so he made a ton of money on the stock market, but his passion was solving these chemistry problems. So that's why he funded this whole effort.
That's right. Yep. And part of his team, at least until recently, was a professor at MIT, who I believe has now also gone back to some university in California. So so it's a fascinating story. And it's why I was hoping he'd show up at HPC on Wall Street one of these days and say, there's a place for HPC on Wall Street. There's certainly a place for HTPC on Wall Street. I mean, you go to the vendor's room down there and people are overclocking their commodity servers, and selling them without a warranty. It's pretty crazy. So look, I'll tear through my last couple of slides. This is kind of so the old paradigm, and we've talked about it here a lot. When the Beowulf book came out and the Beowulf cluster movement started, it looked like a way to solve. People couldn't really figure out how to do the compute communication overlap sufficiently to ever make anything more than a memory bound problem. And this has perpetuated until today. People said, okay, well, let's divide this problem up. There's no reason we should have to do make -J1 to everything. Let's divide the job up. A lot of this stuff is parallelizable. We'll totally kill Amdahl's law because, if Amdahl's law is going to choke you when you've only got 8 computers, well, let's have, like SuperCloud has, let's have 380,000, cores. And then Amdahl's law probably won't kill you because, first of all, nothing ever goes from many to one anymore. I can't think of a scenario. Every processor is multi-core now, so it's not like with an SMP kernel, an OpenMP kernel. So where things are going from many to one, I don't know if that exists anymore. So what folks decided to do in the embarrassingly parallel business is like, hey, we got these 64-bit widths. Let's send 2 floats down it instead of 1 double. We'll get to double if I need to submit my document to you and have my statistician sign off on it that it's in native double precision, we'll do that. But in the meantime, I'm going to get 2x the performance because I'm doing either 2 floats and then iteratively finding it back to double precision, or what they're doing now is all these exotic precisions, B float. There's plenty of people doing AI and ML in integer, and I don't know if you can do 1 bit, but they're probably going to try it. So
int 8 is where it is now.
Is that right?
Yeah. There are like a bunch of things using, and then I think float 8 is also being looked at, like where you just have 1 bit for the exponent and then everything else is mantissa, because for a lot of these things the whole range is between -1 and +1, so they don't need a bunch of exponent bits.
Oh yeah, yep. There's only really, so there's 2 or 3 kinds of research that do need the that dynamic range. I understand that if you're a black hole researcher, you need like octal precision or something crazy like that. So
yeah.
Other than that,
no. But if you just want to determine if a picture is of a cat, 8 bits is enough.
Yeah, I hear you. Okay, so what I think I might do, this is a picture of me when I worked at Microwave. This is okay. So this is certainly pre-GPU. I think this is just when Opterons were coming in, and thanks to AMD for the Opteron revolution, because that really allowed people, dopes like me that could only do 32-bit operating systems and 32-bit applications, to actually screw around with 64-bit applications before. Or actually, it was the other way around, right? You could go from legacy mode to long mode because you could get a 64-bit operating system. I didn't have to figure that out, but I did have to figure out 64-bit applications. So, so we were.
You had alpha. You could do that before, or MIPS.
Well, you couldn't do the mixed mode like you could do with Opteron.
Yes.
And so what people were doing were they were buying these Opteron systems and fielding their 32s. And then eventually growing into, into long mode.
Yeah.
And to make things even better this is back when we were putting socketed chips in and pulling them out. So it wasn't like you had to upgrade the entire machine to get 64-bit applications running. So this was definitely the smart thing to do. It was so smart that Intel ended up licensing it from AMD. So, yeah. So I think what I'll do now that I know, now that I've seen Shankar's slides, I think I'm going to put a full CXL tutorial together with, and Jabber, I'll work with you. Maybe before the end of the year we can do that. But in the meantime, I will stop sharing my screen here. That's oh geez, perfect timing.
I mean, CXL, just to expand on what you said, Kurt, like I think a lot of these mega data centers, right, cloud providers are looking at CXL.mem very, very closely. Because like you said, so many applications need large amounts of memory. And as we see the shift basically from DDR4 to DDR5, they're thinking they can have CXL modules they can then put down all the old DDR4 DIMMs that they already have, right, onto these riser cards and expand their memory pool, and then eventually replace those with all DDR5 down the line. So they have these controllers that can do both DDR4 and DDR5 with a CXL bridge, essentially.
Yep. And unless you're part of that 2% of GPU rich out there, you ain't getting any shipments of any any Hopper systems this year.
Yeah.
I know lots of universities that are in the queue, and they can wait. They can wait until after GPT-7 or something. That's seriously, that's what they're in line with.
Yeah.
Elon Musk bought the entire run of GPUs 1 year, and it was like, how do you compete with that kind of leverage, right? So, so we'll have to
Apple
wait.
bought all of TSMC 3 nanometers, so
That's
it's you have to deal with that. Yeah,
that's right. Get in line.
Yeah.
All right, Professor G. I think maybe, let me see who's here. I see Matthew from formerly from San Diego, now from Austin. If Matthew Mikhailov wants to introduce himself. I don't think we're going to get a San Diego presentation tonight, though, Matthew. So.
Yeah, bummer to hear about that. Hi, everyone. I'm Matt. As Kurt mentioned, I was on the UCSD supercomputing team. I was our team lead for a while, the undergrad team, and now I'm working in hardware design over in Austin. So nice to meet you all. I can introduce you to the new supercomputing folks. Hopefully, they'll be able to present one of these meetings. But they're still going ahead with all the competition. So they'll be competing in this year's student cluster competition, and then there's a new competition that we set up last year that they're planning on continuing, which is called the Raspberry Pi Cluster Competition. And the goal is to sort of lower the barrier to entry to cluster competitions in general. So the student cluster competition, we love it. We love to compete every year whenever they take us. But the hardware costs are really high. And so the goal of the Raspberry Pi Cluster Competition is to make it cheaper for teams that can't quite afford to go to SCC. So anyway, if you have questions about that, I can connect you to people who are doing that. Otherwise, I'm just doing hardware design at the moment. And nice to meet you all.
Yep. Matthew's team won it last year. They had an AMD system. Are they doing AMD again this year, Matthew? I think they are.
Yes, they are. I'm very happy, actually, to hear that they're going with AMD again. Yeah, we had a wonderful experience.
Yep.
Yeah, Jerry, you should probably stop the streamings now.
Okay.
Yeah, because we'll hand it off to Professor G. We have one